Good morning. We are about to go over chapter 9. Not in its entirety. We're going to leave trigonometry for its own little lesson. We started 9 with a review of radicals, and it is just a review of things that theoretically you've known before, how to take the square root of things. So the bottom line, the analogy that I always make is that we break it down into factors and look for pairs. I always say that it is square root prison, and in order to break out a square root prison, all you need is a friend, but only one of you is going to make it on that outside. So 6 and 6 are friends. They make a break for it. One of them makes it out alive. And 2, much like Mr. Greer from the math department, has no friends, stuck in square root prison. And now that is recorded and on record. The number one mistake that we often see is people will do something like, 9 plus 4, and say, okay, well, that is 3 plus 2. The square root of 9 is 3, and the square root of 4 is 2, and that is not the case. You cannot distribute square roots across addition signs. So please do not make that blunder. The other thing that we did a fair amount of was reducing radicals. So if I had something like 1 over square root of 2, which pops up a lot, I'm not allowed to have a square root in the denominator, so I'll multiply both the top and the bottom by square root of 2, and then on the top I'll have square root of 2, and the bottom, root 2 times root 2 is just 2. I have a little trick for dividing things by the square root of 2. This is really 1 divided by the square root of 2. My trick is just to divide it by the normal number without a square root and multiply on a square root. Notice that those two things are really the same. Okay, section 9.2 was Introduction to Circles. I have no idea why the book decided that it needed to introduce circles right there, exactly 1 chapter before it actually does circles. So we're going to skip to what the book calls altitude on hypotenuse and what we lovingly call Fibonacci. The book gives you some formulas, which I do not. I feel like the formulas, they're easy enough to memorize, but they're way too easy to forget. And so I just walk you through the process every single time here. And the process is, and it's called altitude on hypotenuse because it starts with a right triangle, the only triangle which has a hypotenuse, and an altitude drawn to the hypotenuse, and altitudes always form right angles. This angle, shockingly, is congruent to itself. This angle up here is congruent to itself. And if you've noticed, I have 3 triangles. I have the large one, which has a right angle, a hoop, and a notch. This one right here, which I'll call the small one, which has a right angle and a hoop. And so according to that no choice theorem from chapter 8, the third angle has to be congruent to this guy's third angle. Likewise, the medium-sized triangle, its third angle has to be congruent to this one's medium. And so now we've shown through AA, or in fact AAA, that all 3 of these triangles are similar, and we can start solving for different side lengths based on proportions. So the example that I usually give is I call this for this 9 and this x. I insist that people draw out all 3 triangles in the same orientation, 1, 2, and 3. All with their right angles in the same places, their hoops in the same places, and therefore their notches in the same places. It turns out that the big triangle isn't particularly useful. All I know is that in this particular example, its hypotenuse has a length of 13. In the medium triangle, the side opposite the right angle, I know nothing about, but the other 2 legs I do. So opposite the notch is 9, and my other leg, the one opposite the hoop, the one between the notch and the right angle, all good ways of thinking of it, is x. Sorry, I wrote a 4. Likewise, down here I have an x, and a 4, and I can write my proportion. The left side is to the left side as the bottom is to the bottom, or the left is to the bottom as the left is to the bottom. Either way, I come up with the same proportion, and it looks like x over 4 equals 9 over x. If a proportion exists, then you can cross multiply. X squared equals 36, and x equals 6. Algebraically, it would be plus or minus 6, but obviously the negative one doesn't make any sense. All right, that is the basic form. Needless to say, the x's and the given information could be anywhere around there. We went through the process of a super-hoopa, which is a little bit more involved to get into here, to prove Pythagorean's theorem. Pythagorean's theorem, of course, you are probably well aware, says that if a triangle is a right triangle, then a squared plus b squared equals c squared. A squared plus b squared equals c squared. Or if I look at the converse, it really says if a squared plus b squared equals c squared, then the triangle is a right triangle. If a squared plus b squared is greater than c squared, then it's a cute triangle. And if a squared plus b squared is less than c squared, then it is obtuse. All of that information is right here, page 385 in the book. That looks a little out of focus, perhaps. There you go. Right. Needless to say, most of our time in Pythagorean theorem will not be spent with the actual theorem and deciding whether things are right, obtuse, or acute. But for finding lengths, this works all over the place. Anytime that you see a right triangle, even sometimes where it's a little bit hidden. One of those examples are where we look at a rhombus. Sorry, get my finger on that one. And notice that the diagonals are perpendicular, in other words, form right angles, in other words, form right triangles. The diagonals also bisect as they do in any parallelogram. So if I were to tell you that this diagonal had a length of 5, then 10, then each half would be 5. This diagonal has a length of 24, then each side would be 12. And we can play around with Pythagoras and figure out that the other side is 13. Now, hopefully, eventually, when we get to the later sections, you won't need to do that. The next section was a special example of Pythagorean's theorem, which is really just the distance formula. It tells me the distance between 2 points, basically by forming this right triangle and looking for the hypotenuse of it. So this length right here would be the change in x. This one right here would be the change in y. And so my distance is obtained with the Pythagorean theorem. Distance is the square root of the change in x squared plus the change in y squared. I like that formula for starting this problem. I'm also okay with just calling this D, calling it C, and saying that C equals a squared plus b squared. This takes a little bit out of the work out of that, and that it already has the square root where you want it. There is another form which makes sense. It's just harder to memorize because it has that little subscript. If I were going to call this point x1 comma y1, then this one would be x2 comma y2. This length is that change in x. It is x2 minus x1. And this is the change in y. It is that y2 minus y1. So using those instead of the change in x, I end up with the square root of x2 minus x1 quantity squared plus y2, thank you, Kat, keep moving, minus y1 quantity squared. Okay, moving on, we moved into some reduced triangle and some shortcuts. So the property of reduced triangles, come on, Katie. Thank you. Yes. The property of reduced triangles just makes life a little bit easier for yourself when you're using Pythagorean's theorem on some gnarly numbers. Like, for example, if I told you that this had a length of 11 and this had a length of 77, right triangle, and asked you to find x. Well, I would say nerds to that. That seems difficult. What I'm going to do instead is I'm going to draw the similar triangle with a length of 1 and 7 and maybe figure out what y is. Cat, you're really not helping anyone here. Come on. This looks pretty easy. A squared plus b squared equals c squared is always a good way to go. 1 squared plus 7 squared equals c squared. 1 plus 49 equals, I guess, y squared. 50 equals y squared. And y equals 5 root 2. Well, now that I figured out what y is, how does it relate to x? This triangle is similar. The lengths are proportional. That ratio of proportionality is 1 to 11. So it's just going to be 11 times bigger. It's going to be 55 root 2. Okay, speaking of similar triangles, there are some famous ones. They are basically listed on, really in the homework on page 401. The most famous of them is the 3, 4, 5 triangle. So the bottom line here is if you see a 3 in this position and a 4 in that position, you know that this is 5. Or if you see a 5 in this position and a 4 in that position, you know it's 3, etc., etc. Or any scale multiple. For example, maybe I give you that this is 20 in the hypotenuse, which is 5 times 4. This is 16, which is 4 times 4. Well, my missing one must be 3 times 4. My missing one must be 12. Okay. The other Pythagorean triples, as they are the 5, 12, 13, the 7, 24, 25, and the 8, 15, 17. Okay. Those are the triangles which are famous for the lengths of their sides. The other two in the next section are famous for the measure of their angles. The other two are the 45, 45, 90, which is the only isosceles right triangle out there. Basically, it always looks like x, x, x square root 2, or the 30, 60, 90 triangle, which is probably the most famous of the bunch. And it looks like x, 2x, and x square root 3. Ways in which I try to help people remember it. In the 45, 45, 90, there's 2 different side lengths. There's either x or x root 2. The root 2 kind of reflects the fact that there are 2 different side lengths. Here there are 3 different side lengths, and I end up with a root 3. It's as easy to remember as 1, 2, root 3. We did a lot of work in finding one side length based on the others for these. Definitely a doable process. And the last section that we're going to cover right now is the 3-dimensional Pythagorean's theorem. Just to get it out there, it is distance is the change in x squared plus the change in y squared plus the change in z squared. If I give you kind of the simplest application of that, if we look at some sort of shoebox, tissue box looking thing, and we move from this corner to that corner, well, I moved across the page a certain amount, maybe 10. I moved into the page a certain amount. maybe 4. And I moved up the page a certain amount, maybe 5. The distance from this point to that point would equal the square root of 10 squared plus 5 squared plus 4 squared. Order doesn't really matter here. So just to finish this one, that would be the square root of 100 plus 25 plus 16. That is the square root of 141. Okay, that is it for this part of chapter 9. We will do trigonometry next.